Okay, so this comes now. So Rishi will continue the second lecture of probing non-standard physics using particular.
Okay, so one piece of new physics that we know for sure exists is dark matter. Right? Dark matter does exist. So far, the only thing we know about dark matter is that it has gravitational interactions. Beyond that, we don't know much more. Right? So, we know about dark matter is that it must be cold. So it should be a particle or composite particle or some other massive entity like primordial black hole. It has to be massive. And it has to be non-relativistic. It obviously has gravitational interactions because everything interacts with gravity, gravitationally. Right? But other interactions with the standard model particles must be very weak. Right? So, interactions with standard model particles should be weak. In particular, interactions with photons or electromagnetism should be weak. That is why it is called dark. Right? And the non-relativistic means that its kinetic energy, when we measure it in eco-moving frame, should be much smaller than its mass. So these are the properties we know for sure, but beyond that we don't know much about it. So the field is actually wide open, and there are many theoretical possibilities. The range that dark matter can have just in mass is enormous. Right? So its mass can start from anywhere between 10 to the minus 22 electron volts all the way up to solar masses or even this is an enormous range. Okay, so this is, so neutrinos are, the mass of neutrino is around 10 to the minus 2 electron volt, probably the lightest neutrino. That is the order of magnitude that we have, and this is 20 orders of magnitude smaller is allowed. Right? So smaller than that is not allowed because then the wave function of the dark matter becomes of the size of galaxy and we cannot really form galaxy. So galactic physics puts the lower limit, and the upper limit comes from around solar masses or primordial black holes. There are many constraints. So there are small windows here at the highest range of higher range of the masses where you could have some black holes are allowed, but some part of it, this parameter space is ruled out from micro-lensing or non-observation of, if there are very massive black holes, they should accrete matter around them. So just by counting the number of black holes that we see, you can rule out very high mass black holes or solar mass black holes. Asteroid mass black holes are allowed. So it's a huge possibility. So now how do you go about searching for this dark matter? So how should we think about this? This is a huge possibility and you can't look everywhere. So I will disregard the massive objects like black holes or meteors or other things. I will assume that it is a fundamental particle or a mixture of fundamental particles. These are some made up of some new particles, or particles beyond the standard model in particle physics. So that is that. Then we can ask, okay, what kind of, so how do you define a particle, right? So particle is defined by its fundamental properties, mass and spin. But beyond that, what you need to define a particle, what particle is defined by its interactions with other particles and with itself, right? Or by the charges it carries. The interactions are just charges it carries. So charges or interactions define what a particle is. So we want to know what charges this dark matter carries, or what are these interactions with other particles in the dark sector or particles in the standard model. So in particular, there are actually particles in standard model which could have been a nice dark matter candidate, but they have problems, right? One example is neutrino. So neutrino has all these properties, right? It is massive, and its interactions with other standard model particles are very weak. They are actually weak interactions. But it violates this property, non-relativistic. So it becomes non-relativistic much later, which means it is not a cold dark matter, it is a hot dark matter. And that has problem with structure formation. You cannot start forming galaxies early enough. So the number of galaxies that we will see if neutrino was dark matter would be very small. Right? Neutrino is an example of a what could be a dark matter that is a fundamental particle, right? But it will also be a composite particle. So another example is neutron. So neutron also is neutral, does not carry any charges, right? So if neutron was stable, it could also have been a dark matter candidate. So it again satisfies many of the properties, but it will actually also have strong interactions. So it will spew up the Big Bang nucleosynthesis. The neutron was dark matter, and plus it is not stable. So dark matter has to be stable. Maybe we can write that also here. Stable or on the order of 8 of the universe. Its lifetime, even if it is not stable, its lifetime should be bigger than 8 of the universe. So that we don't see any decay until now. So neutron has, I think, lifetime of about 3 minutes. So it is an example. So dark matter can be, you don't really have to think of it as a fundamental particle. It can be a composite particle. So dark sector does not need to be just a single particle, single new particle in some standard model. Dark sector can be as complex as the standard model, and it can be, dark matter can be a very complicated composite particle, just like baryons or neutrons and protons or nuclei. So one way is to, you start from a particle physics model, you put up some model, okay, what can dark matter be, and then work out its observational consequences. Right, so that is the bottom-up approach. Another way is that you already look at observations first and see if you see any anomalies. And then you see, okay, what kind of, these anomalies means that something you see in observations which cannot be explained by any standard physics, even if you change your reionization models or even centimeter models. Astrophysics, you cannot explain that anomaly. So then maybe that is probably caused by something happening with the dark matter, or dark matter interacting in some complicated way with the visible matter. So then you ask, okay, what kind of dark matter you will need in order to explain that anomaly. That is the second other way. Right? So let us look at the example of this by looking at tensions. So we already know what one such anomaly which cannot be explained by anything, and that is this Hedges anomaly. So let us look at what is anomalous about Hedges signal. Right, so Hedges is a measurement of a global spectrum in around 70 megahertz, 60 to 90, sorry, 60 to 90 megahertz. Right. So what I observed is a difference in brightness temperature, delta TB. And I think you have all seen these formulae many times. TCMB or T radiation, whatever the background radiation is not CMB. We can write this as PS minus PR over the reactive in terms of spin temperature and the radiation temperature and then some optical depth. If the optical depth is small, you can just it just becomes proportional to optical depth, where optical depth is proportional to the number density of hydrogen atoms, the nuclear hydrogen, transition strength, and then there are factors of frequency and Hubble and spin temperature. As we have all seen this formula before. So what I just saw is something like this, between around 60 megahertz and 90 megahertz. Right. So there are two anomalous features in this kind of a spectrum that the IGS sees. One is that these are very sharp IGS here. This one and this one. And then this amplitude is anomalous. So this is around 0.5 Kelvin. So, whereas in the standard model, whatever you do, you cannot get more than 0.2 Kelvin difference. Right? Even if, and this is just given by the fact that there is a lower limit to how cold the baryons can be in the standard model. Okay, so we have anomalous amplitude. There are two anomalous features. One is and second is, you could say, unphysical or unphysically sharp edges. And if you look at papers which try to explain, add new physics to explain this edges anomaly, usually the spectra they get is something like this. So they don't get, almost no one gets these sharp edges. In the spectra that you see, even in the standard cosmology, where the amplitude is less, or even when you add some new physics, the spectra that you see is something like a conical shape or sharp dip, and then you never see this flattened profile. So this is very, very hard to get. Right? And in fact, there is a Saras experiment by Saurabh here, who was giving lectures on experiments. And Saurabh looked for this particular feature, the particular profile in the Saras experiments, and they failed to find this. So they actually rule out that this profile is actually there. Right? So it means that this profile is more or less most likely a systematic, it is not real. But that does not mean there is no signal here. It is possible there is a combination of systematics, and so when you remove the systematic, there might still be some signal left here. So Saras does not rule out that there is no signal here. The only thing they rule out is that this particular flattened profile, that is not there, at least as far as Saras experiment is concerned. But there could still be some other signal which may still have anomalous amplitude, maybe not as large as 0.5 Kelvin, maybe 0.3 or 0.4. So anything bigger than 0.2 Kelvin would be anomalous. And it cannot be explained, does not matter what you do in standard cosmology, you cannot explain if the signal dip is bigger than 0.2 Kelvin. So we have to invoke new physics. So this is an example of a robust signal. With the next generation of experiments, they confirm there is really some anomalous signal here, and you will actually need new physics. Right? Okay. Right, so how do you get this anomalous signal? So how do you go about thinking about this? And so, so first you have to see where this 0.2 Kelvin limit comes from, why it cannot be bigger than 0.2 Kelvin. And so that just comes from the fact that, so CMB temperature, this is redshift, this is temperature. So CMB temperature is going as 1 plus Z, right? And the baryons, they decouple around redshift of 200, or around 200, up to 200, the baryon temperature is almost same as CMB temperature because of Compton scattering. So this is our standard model. After that, they decouple. So recombination is happening at 1100, right? So the photons decouple from baryons at 1100, but baryons are still thermally coupled, right? So the decoupling at recombination is not symmetry. So photons forget about baryons, that baryons exist after 1100 and they are just free streaming to us. But baryons are still coupled because this is just coming because the number of photons to number of baryons is enormous, right? 10 to the 9. So for each baryon there are enormous number of photons. So baryons still feel the photon pressure and they still feel Compton scattering, which keeps transferring energy from CMB to the baryons. Because of the large entropy, you just have to get little bit of energy to bring their temperature to the same level. So up to 200, actually up to 500, it is almost completely coupled, and then they start decoupling between 500 and 200. Right? And now after 200, the baryons start cooling adiabatically, they are completely decoupled. So this goes as like this, 1 plus Z squared. Right? So now this is happening around redshifts of, I forget, 20 or so. Right? Which means that this difference between the baryon temperatures and the CMB temperature, this is fixed. It cannot be bigger than that in standard cosmology. This is the maximum you can get. To get the maximum signal, you have to couple the baryons to the spin temperature to the baryon temperature, which means usually the spin temperature would be something like this. Suppose you cook up some astrophysics so that the spin temperature gets completely coupled to baryon. So the lower the spin temperature can, so there are only two temperatures here, CMB and baryons. The spin temperature has to lie in between. The biggest signal you will get is when the spin temperature is smallest, and the smallest spin temperature can be the baryon temperature. If you put the spin temperature equal to baryon temperature in that formula, the brightness temperature that you get is around 0.2 Kelvin. Now you want to get 0.5 Kelvin from 21 centimeter, then you have to cool baryon faster than this. Right? So how do you cool that? So this was the idea by Barkana, which paper came simultaneously with the edges, that the only thing which is colder than baryons is dark matter. Right? So dark matter decoupled much earlier from the CMB, and it has been cooling adiabatically as 1 plus Z squared, the kinetic temperature of dark matter. So once you decouple, you just non-relativistic particle just cool as 1 plus Z squared. So it has been cooling adiabatically. Okay, maybe we can use the different colors. Right, from very early times, at redshift 20, this dark matter temperature is actually almost 0, or close to 0. It's very cold. So if you can introduce coupling between baryons and dark matter, then you can cool the baryons further, right? And then the spin temperature is coupled to the baryon temperature, so then you can go much below 0.2 Kelvin. So that this dip can be much bigger. But there is a problem here, right? Because the number density of particles is decreasing as 1 plus Z cube with redshift, right? And these interaction rates, they depend on density or density square, right? So you have some cross section, and then the interaction will n times sigma, which means that you are tightly coupled here, you have even more tightly coupled here at earlier redshifts. So you are very tightly coupled at earlier redshifts, then that means that the dark matter temperature will become equal to CMB. Right? So it is not just, so the coupling happens, so you are cooling the baryons, but at the same time, when you couple baryons and dark matter, so dark matter cools the baryons, but baryons also heat up the dark matter. Right? There is an energy flow from dark matter to baryons to dark matter. So baryons at a higher temperature. We are cooling baryon, but we are also heating up dark matter. But in this, and here you can do this because you are decoupled from CMB. Right? But if you couple dark matter, if you put a large cross section, then you will be coupled. The dark matter and baryons will be coupled together at high redshift, so they will have same temperature. But baryons have same temperature as CMB, right? Which means that the dark matter will just follow the baryon temperature, and then you don't gain anything. Right? So some fine tuning has to be done. So just putting it an interaction between dark matter and baryon does not work. Interaction has to be a particular kind. So the idea was that the interaction should have a velocity dependence, and it has velocity dependence to the -4. So this is basically what is you have a Rutherford scattering. The Rutherford scattering or the Coulomb scattering, it has a velocity dependence which is v to the -4.
So what does it physically mean? Dark matter have a temperature?
So that is, so temperature just means that so when dark matter was coupled, it has some thermal distribution, right, at early times. So temperature is just.
But we don't know if it is a particle or what.
No, so here I am assuming it is a particle. So here I am assuming it is a particle. Then it has some, when it was coupled, it has some temperature. So when you decouple, right, so it has a Maxwellian distribution, right? You start with a Maxwellian distribution and then you decouple, and the expansion does not change the distribution of particles. So it will remain a Maxwellian distribution with the expansion, and it will just, temperature will just go as 1 plus z square. Even if there is no interaction with dark matter, just because all velocities are, right, so all velocities, the scale as 1 over a. And the velocity is redshift as 1 over a. All the momenta of all particles, relativistic or non-relativistic, the redshift as 1 over a. Right? Because all velocities are redshifting, so the Maxwellian shape is maintained, which the temperature just goes as 1 plus z square. Right? So if you have a Maxwellian distribution, it is e to the minus v square over t. Right? So the distribution does not change. So this is the occupation number or the phase space density. So there is a theorem in general relativity called Liouville's theorem, which tells you that occupation number or the phase space density is invariant. So even when you are expanding or you are lensing along the geodesics, the phase space distribution remains invariant. So if the velocities are all redshifting as a, and this has to remain invariant, that means t has to redshift as 1 over a square. So that is where 1 plus z square dependence comes for both baryons and the dark matter. Whereas the CMB, the occupation number is the Planck spectrum, so it is e to the minus h mu over kt. So here the frequency is redshifts as 1 over a, which means temperature must also redshift as 1 over a, so that the occupation number remains invariant. So that is why CMB has a redshift dependence of 1 plus z.
So here dark matter is behaving as ideal gas, like
So it is a non-interacting ideal, Poissonless ideal gas.
Then what is providing it pressure? Because dark matter is.
There is no pressure. So pressure is just kinetic energy, right? Particles have kinetic energy.
So it cannot do that. It cannot like pressure what we define.
Yeah, so we are assuming it is pressureless, which means that there are no interactions within itself
Just
or with the baryons.
Thermal.
It is just the velocities. They have a velocity distribution. So temperature just tells you that they have a non-zero peculiar velocity distribution. That's all it means.
I couldn't follow that part where you said that decomposition should be earlier or something. I mean this.
So dark matter decouples in standard model much earlier. Right? That is why it is called dark matter. It decouples even before the BBN. It must decouple, otherwise you will destroy the BBN predictions. Right? So dark matter must decouple at redshift of 10 to the 9 or so. Right? If it is coupled later on, if it is coupled to baryon, then you destroy the CMB predictions also. So CMB requires that at the time of recombination or even before that, the dark matter must be decoupled from baryons and photons. Right? If it is not, then dark matter will also participate in the oscillations. So it will behave as baryons. You will get a much bigger omega baryon. Right? So to be consistent with CMB and BDN, between BDN and recombination, the dark matter must be decoupled.
But then the spin temperature will follow this dark matter temperature, and what is the baryon temperature be? Kinetic temperature be?
Okay, anyway, we come to. So there is a standard model thing that is. So standard model, this is happening. At redshift of 10 to the 9, this dark matter decouples. So this is dark matter. Right? This is CMD. Right? And baryons remain coupled at up to 200, and then they decouple. Right? And then in the standard model, spin temperature will follow baryon temperature for a while, then it decouples. But then you have Lyman alpha coupling again, so it couples again. Right? So this is what spin temperature is doing. So here the maximum thing you can get is 0.2 Kelvin. Right? This is what is happening in standard model. So now we want to couple baryons to dark matter, but we don't want it to couple too early. We want it to be remain decoupled up to 1100, right? But after 1100, we want some interactions between dark matter and CMD, dark matter and baryons, so that dark matter can cool the baryons.
So CMB is falling as 1 by Z.
So if we at 1100, we turn on the interactions between dark matter and baryons, right? Which means that the baryons can start cooling not 1 plus Z square, but because they are also transferring some energy to Dn, they can cool faster than 1 plus Z square. Right? So dark matter temperature can do something like this, baryon temperature with interactions. With baryon dark matter interactions, if you couple baryons and dark matter, we can transfer some of their energy to dark matter. So baryon will do something like this. Dark matter, you are cooling baryons, you will heat up the dark matter. So dark matter will do something like this. Right? So the end result will be that the spin temperature now can come much smaller than. Right? So spin temperature can be much smaller than 0.2 Kelvin difference here. So the brightness temperature can is smaller than 0.2.
Sir, the CMB is following 1 by 1 plus Z.
CMB is following 1 plus Z, yes, always.
But dark matter is following. Is it same 1 by 1 plus Z?
No, so dark matter, this will be 1 plus Z square. Right? So non-relativistic particles, their adiabatic cooling is 1 plus Z square. Relativistic particles, the temperature falls as 1 plus Z. Right? And this is just comes from this variation of occupation number. You have the phase space density, you have Maxwellian distribution, you have V square over T for non-relativistic particles, and for relativistic particles you have nu over T.
But for something to couple with the dark matter temperature, it cannot be cold dark matter, right? It should interact otherwise, correct?
Yes. So you have to introduce the interaction. That is a new physics that we are adding in. So lambda CDM, there is no interaction. Right? Now we are adding some new physics. So we are adding an additional interaction between baryons and dark matter, so that baryons can transfer some of their energy to dark matter and they can cool down below the adiabatic limit. This is the adiabatic limit for baryons. So they can cool below that their adiabatic temperature of lambda CDM. Yeah?
So there will be some signature of this in the baryon acoustic oscillations also in the early.
Yeah, so that depends whether so where they decouple, right? So where or when they couple. So if they couple late enough, then you will not have any signatures in BAO, because BAO stop, the acoustic oscillations stop at recombination. So if you have to recombination, they are decoupled, then there is no signature. But if you couple them, so that is the constraint. That is why we want them to be decoupled until recombination. Because if you are coupled, dark matter and baryons are coupled before recombination, then you will see their signatures in acoustic oscillations. The acoustic oscillations will get modified. So the dark matter is also oscillating.
So this new physics, there shouldn't occur also in the much earlier universe.
It should not occur at early universe, yes. It should only turn on after recombination. And the way to do this is by making the cross section velocity dependent. Right? And these cross sections are there. Coulomb scattering has actually this cross section. Right? So at early times, the velocities are large, which means the cross sections are small. So you are decoupled. But after recombination, velocities have the velocities are redshifting as 1 over a. So at some point, the velocities are small enough that this cross section becomes large. So this is the cross section between baryons and dark matter. Right? So which means they start Coulomb scattering with each other. So the way to get this cross section, this is a Coulomb cross section. So the easiest way to get this is by giving a milli charge to dark matter. So this you get. This was Abhagana's paper that you give a milli charge to the dark matter. Milli charge means that the Q dark matter has a charge which is 10 to the minus 3 or 10 to the minus 7. I forgot the exact number, but milli charge, so much smaller than the charge of electron. We are giving it a very tiny charge that gives us just from Coulomb scattering, some scattering cross sections. And elastic scattering between dark matter and baryons will pull the baryons down. It turns out this does not really work because the cross section you need, the amplitude of the cross section you need is still large enough here that you are actually not completely decoupled by recombination. So the amplitude of the cross section that you, so this dependence is not enough, it turns out, to decouple, the dark matter will be decoupled by 1100. So it does not quite work. So then they said, okay, maybe not all of the dark matter is milli charged, only a small fraction. So only F milli charged dark matter is maybe 10 to the minus 4. So only a very small fraction of dark matter is milli charged. Right? Thus dark matter is completely uncharged or has no interactions. So then it turns out that okay, maybe you could get this signal, but then turns out there are other problems with this. And this also actually does not quite really work. So I am not going to all the problems. I will, so this is a paper I will refer you to if you want to look for details and particular what are the problems with this kind of scenario. This is 1803.02804. This is the archive number. This is I think Berlin, Hooper, and others. But even after doing all this, what you get is a signal which is something like this. So you don't get a flattened shape. So to get a flattened, yeah.
So did they completely disregard the limits from directed action experiments?
No, yeah, so they are all there. So that is this paper discusses all those limits. So which is why you get this. So when you have a small fraction, then you can evade the direct detection limits also. Right? Because only a small fraction of dark matter is milli charged. Most of the dark matter is uncharged. Right? So the limits get weakened by a factor of 10 to the 4. But it turns out you don't completely evade all those things. So again, yeah, so I think initial paper they thought they are evading all these limits, but it turns out that I think some limits are still there, so it does not quite work. So when you combine all limits from CMB, BBN, and drag detection, then you rule out most of the parameter space. I don't remember which limit was the most stringent. But all these limits apply, you are right.
And the mass is a free parameter for them.
And mass is a free parameter also. Yeah, so the limits are a function of mass. So you look for in mass cross section space, right? Or the mass, so you look for, so the milli charge epsilon, right? Okay, what fraction of electron charge is the charge? So Q equals epsilon times E and mass. and you look for, whether there is a viable space in this limits. So you have drag detection limits, you have median limits and CMD limits. And you see whether, and then this fraction of dark matter can be another parameter. Like you try to see whether there is a parameter space which is allowed by all the other limits, and you can still give you this kind of pooling. It turns out, so I don't remember exactly. I think either all of parameter space is ruled out when you take into account all limits, or there is some small parameter space. It means a very small mass range or absolute range limits where you could get. But even after doing all this shape you get is something like this, right? So this is the high redshift range, right? This is the low redshift edge, right? So now you can ask, okay, what you need to do? So by coupling this, you can get an anomalous signal, right? So this is a Milling chart, but you can have other kinds of interactions. But the main idea is that you should have dark matter baryon elastic scattering. There is some interaction between baryons and dark matter, so that elastic scattering you can transfer energy from one to the other. That can give you the amplitude, but to get this edge, you have to actually, so this edge is coming on the high redshift side because stars start forming and they have flood the universe with Lyman alpha that decouples the, so in the normal models, this star formation will start slowly, right? So to get this edge, you actually have to suddenly flood the, you should have a sudden burst of star formation that suddenly floods the universe with, so fast, flood the universe with Lyman alpha photons. Fast Lyman alpha production. And you can ask how physical or unphysical that is. And to get the right edge, you have to, the signal has to disappear again. So one way to do that is to remove all the Lyman alpha photons, which means you suddenly stop star formation activity here. Right? So you could remove somehow, let us say remove. So these Lyman alpha photons would have redshifted, and we are producing no new Lyman alpha photons. Suddenly, to stop all star formation activity or the, but that is difficult, right? Once you stars form, they will shine for a long time. The other way is that you heat up the gas. Right? So you heat up the gas above the CME temperature, then also this absorption disappears. But again, this heating has to be very, very fast. Okay, so Shikhar is sitting here. Shikhar and Girish have actually written a paper on this, exploring these, I think, especially edges, how physical or unphysical that is. So I will just, you can ask him or read their paper. Mittal and Kulkarni. When was this? Last year? 2022. Right? So they discuss in detail what you need to get these sharp edges and how physical or unphysical that is. So I think both from theoretical difficulties and also from the source experiments, which is most likely that these edges, particular shape will disappear, but maybe some signal will remain, and then that may would be exciting. So we have to wait for next experiment to see that. How will we do much time? Okay.
So I have seen a paper on cosmic ray heating to explain the IGC.
Yeah, so this is, so cosmic ray heating.
Excess heating from cosmic ray.
Sorry?
Excess heating from cosmic ray.
Yeah, so excess heating can give you this edge. But you still have to produce this amplitude, right? And I'm not sure how cosmic rays will do that. Just heating is not enough. So another way is, so this, this difference, so edges is not an absolute measurement, right? You don't know where the background radiation is. What you see is a, some mix. So what edges observed is some thousands of kelvins of mostly foreground, synchrotron. So you fit a synchrotron model, right? So you remove the synchrotron emission, and you are left with some residuals, right? When you try to model these residuals with some signal, then you fit the signal and synchrotron model together, and that is how you get this kind of, right? But here, you don't know whether you are removing the synchrotron, so where the background radiation level is. Right? So in the early universe, if the only radiation is not CMB, but CMB plus something new, some new radiation, right? So let us say after recompilation, there was some dark matter which decayed, light dark matter, which decayed 2 photons, and flooded the universe with some radio background. So then the background with respect to which you are absorbing is not the CMB, but something else, which is much higher. So Tn is much higher, then also with the same spin temperature, you can get a much bigger difference. Right? So that is the another way, second way to explain that. Again, you need a fast heating. So what is the good explain the fast heating that you need? You still need fast star formation to flood the universe with laminar copper. Okay. So this is one example, but of a robust signal, and also I think this is an interesting example, even if the signal is not real. It is an interesting example to study because it tells you all the things that you have to take care of, all the constraints, because there are lots of experiments and lots of cosmological data, and any new physics that you propose has to satisfy all the existing constraints and then explain also the anomaly. There are difficulties. So it is not easy to add new physics because we have a lot of data now, which must be satisfied. Right. So this dark matter baryons is one example, but there are so you can ask, okay, what else can you learn from 21 centimeter about dark matter? So this is one example where, okay, if dark matter is interactions with baryons, then you get some signal. But in general, so there are many possibilities. So you can have dark matter interactions. Right? So dark matter can have self interactions. It may be decoupled from baryons and CMB, but it can have its own pressure. So right now we are considering pressureless dark matter. So it can have interactions among itself. It may be tightly coupled. That will change the power spectrum. It will change the dark matter profiles. So this is sometimes used to explain the spore curse problem in the center or the missing satellites problem. This was a right. So you can ask questions. Whatever 21 centimeter signal you are interested in, whether 21 centimeter forest or intensity mapping, you can ask dark matter self interactions, how that will change your signals. Dark matter can interact with other dark sector particles. Right? For example, dark sector cannot be just dark matter, it can also have dark radiation. And a small amount of dark radiation is allowed, then that is parameterized by this parameter called N effective. So maybe there is a background of dark radiation, and dark matter is dark radiation. That can also introduce features in the CMB spectrum or matter power spectrum. Right? Because dark matter can feel now the radiation pressure just like barrier feels the CMB pressure. Dark matter, we can look for dark matter interactions with other standard model particles. So not just baryons, but electrons. Right? So all neutrinos, photons, and ask how these interactions will change your signal and whether you can constrain or detect something signature of these interactions in your experiments. Right? So neutrinos are decoupled, like dark matter is also decoupled from baryons and photons. So it turns out that they do have, right? So even if dark matter only interacts with dark sector particles or neutrinos, you still have field effect on the baryons and photons just because of gravity, because you change the perturbations in the dark sector and that affects and the baryons feel the gravity of dark matter. So if something in dark matter is changing, the baryons and photons feel it. So you can still see imprints in the baryons and even in the CMB. The gravity couples everything. But then, so in general, intensity mapping or dark forest, so in particular, if you change the dark matter profiles, then in the 21 centimeter forest, the line profiles, right? So the 21 centimeter lines are coming from the gas clouds in a dark matter potential. Right? So the dark matter interactions, self interactions or interactions with other particles, they change the dark matter profile. That will change the potential in which this H1 gas is, which will change the velocity distribution of H1 gas. Yes, H1 clouds are moving around in the dark matter potential. So the line profile has information, 21 centimeter line profile can have information about properties of dark matter. And I don't think this particular aspect has been explored in literature. I think this is still an open question, how sensitive the dark forest, 21 centimeter forest will be to this new physics.
Is there a possibility it can be more sensitive than CFU due to the saxophone? As well as the saxophone effect also proves the exact same thing, right?
No, saxophone effect is proving the changing potentials, right? But here I am talking about that just the dark matter profile is changed. Right? So you have NFW profile that you expect for CDM. If you have dark matter interactions, it can change from NFW to something else. It can become flattened, right? So which means that the potentials in which the hydrogen clouds are moving, that is different. Which means that the velocity profile of hydrogen clouds will be different. That velocity profile goes into the line profile of 21 centimeter that you see. Right? So the line profile comes mostly from the virial velocity of hydrogen clouds in the dark matter. Right? Because the clouds are very cold usually. H1 clouds have to be cold. The virial velocities are much bigger than the thermal velocities usually, especially in big halos. Right. I think maybe one probably robust feature which I've not seen many papers on this. There are a few papers on 21 centimeter forest, but I've not seen much more as detailed analysis as diamond alpha forest. Diamond alpha forest, people have done much more detailed studies. So that is, I think, interesting idea to explore. And that is probably a robust feature that to look for new physics, the line profile. Because you have a prediction and it does not depend too much on the amplitude of the lines, may depend on the astrophysics, but the line profiles themselves may not depend that much on astrophysics. So that is one example of the robust signal which is insensitive to foregrounds or modeling of your 21 centimeter. The another feature is baryon acoustic oscillations. I think we have 5 minutes. Let me just quickly. So another feature is BAOs. And BAOs are interesting because they provide a standard ruler. So that baryonic acoustic. This one will not matter so far. These are interesting because some of the low-density universe, in particular, they provide a standard or a way to measure the expansion history. So that is a way to constrain or measure dark energy or the evolution of dark energy in time. Right? Let's see. So dark energy can be a new particle, because a new scalar particle that is one of the most, just like inflaton, right, which is causing the acceleration of the universe in some flat potential or flattish potential, scalar field in a flattish potential. It can be a cosmological constant. It could also be a modification of gravity. So if it is a cosmological constant or a scalar field, that would have a different evolution. A scalar field will have an equation of state close to -1, but not exactly -1. A cosmological constant is exactly -1. The first thing that people are trying to find out is whether equation of state is exactly -1 or whether it is a small deviation. Right? If you just detect a small deviation from -1, you have already detected new physics, because you have shown that it is not lambda. It cannot be lambda, it has to be something dynamic. So dynamic can be either some new particle, it could also be a modification of gravity. Or even without dark energy, you can still look for other modifications of gravity that do not manifest.
Why can't the scalar field have exactly -1?
Exactly -1 is a cosmological constant. So usually scalar image is something dynamic. So exactly -1 would be difficult to get from. So the potential is coming from interactions, right? So potential is, so remember your classical mechanics. Potentials are just interactions of field with themselves and with other particles. That is what we do the potential. So potential of exactly -1 would be unphysical, getting from some interaction. So usually you will have small deviations from -1. Right. If it is exactly -1, then this is just cosmological constant. You don't really have indistinguishable. So you can just call it cosmological constant instead of a scalar field.
The deviation from -1 can happen in both directions.
So in principle, yes, but there are problems in the other direction. If it goes below -1, then you are violating some energy conditions of general relativity. Again, so there are ways around that. As long as it is not a fundamental particle but some effective field, then you can have deviations on both sides. So if it is a fundamental field, then you can't really have deviation on the other side. Right, so another way, so before I go to baryon postulation, just one small thing. So another so interesting paper you can look for I hope some of you or most of you have seen this message before. In the Newtonian gauge, even if you not, that is fine. Right? So in the Newton's gravity, there is only one potential, gravitational potential, that determines everything. But in GR, there are 2 degrees of freedom. Right? There are 2 gravitational potentials, phi and psi. And in Einstein's gravity, at late times or at low redshifts, these potentials should be equal. Phi should be equal to psi. Right? So if, but there are modifications of Einstein's gravity where phi is not equal to psi. There is a difference. So one way to look for modifications of gravity, and it may have nothing to do with the dark energy. It may just be a different modification of gravity. Is to look for whether phi is equal to psi or not. And one way to look for is so if you look at lensing of photons, that depends on a different combination of phi and psi, and the growth of structure. If you write down equations for lensing and growth of structure, you will find that they depend on different combination, linear combinations of phi and psi. Right? So they are both coming from the same structure, same dark matter halos. And the same, so they are lensing and those of structure, they are probing the same matter distribution, but they are two different combinations of phi and psi. So if you measure both, then you can measure phi and psi independently, and you can check whether they are equal or not. So this is one way, one example of modification of gravity that you can look for. So again, so 21 centimeter can probe growth of structure. You can also actually look at 21 centimeter lensing. There are some papers, but again, how to go from there to this test of gravity, I have not seen many papers on that. But there are many papers of how to do this with large scale structure or galaxy surveys. That is interesting thing to look at. Okay, so let's go to the baryon acoustic oscillations. So these are just the acoustic oscillations that are happening before recombination. Right? So at Z greater than 1100, electrons and photons are coupled to each other. And so you have electrons, right? And photons are just doing a random walk in a sea of electrons. They collide with Thomson scattering, they're tightly coupled to each other. And this plasma oscillates. And the initial conditions of the universe are adiabatic initial conditions coming from inflation. So when you put in these initial conditions or boundary conditions, you find that so any perturbations, first of all, any perturbations in a fluid, they will oscillate. Right? When I talk, I am perturbing the air, and that perturbation is traveling. So these are sound waves. So similarly, we have primordial fluctuations which are present in this fluid in the universe. These perturbations will oscillate as sound waves, and the initial conditions are adiabatic initial conditions, which means that if you put into the equation that the waves that you get, so these waves are traveling waves, but the sound waves that you get here are standing sound waves. Right? What that means is that you look at particular K modes. So a particular K mode will look something like this, right? Particular K mode just means this plane wave e to the I K dot x. Right? You look at one particular mode, and you see how it evolves with time. So I'm using eta, which is conformal time, but it does not really matter. Right? So standing wave means that as the time passes, this amplitude will oscillate. Right? So standing wave is, something like this multiplied by some cosine of k eta over this is the sound speed. Right? Standing wave, the initial part and the time part are in one cosine. Right? Where in the standing wave they separate out or factor out. So you are looking at a plane wave and the amplitude, so this is the amplitude of the plane wave, and the amplitude is oscillating. So as the time passes, this will decrease, and the wave will remain at the same place. The peaks and troughs, they will not move, because this standing wave or traveling wave. Right? At some point, it will pass through zero, right? And then it will change sign. Right? And then it will. Right? That is how these K modes are oscillating. Then you ask, okay, at time of recombination, there will be some modes which are going through their maximum amplitude. So their amplitude is maximum. Right? So this first mode which is going through the maximum, it appears in the CMB as the first peak. Then the mode, K mode, which is going to a zero at the time of recombination, it will appear as the first trough. Then the next mode will appear as the second peak, and so on and so forth. Right? So the mode which is in the CMB that we see is the acoustic oscillations. The density is oscillating as cosine. And the velocities are oscillating as yes.
So the initial condition necessary to be NL.
Yeah, so here initial condition adiabatic means that all modes are starting with the same amplitude when they enter horizon. And when they enter horizon, after they enter horizon, they start oscillating. you write this as not as this, you write this as K times Rs, where Rs is the sound horizon for each K mode. And so the time is inside this Rs. So KRS is approximately K times CS times theta. So K times RS is the sound horizon, which is how much distance a sound can travel since 0 to time eta, which is just CS times eta. CS is the sound speed. And at early times, if you are radiation dominated, the sound speed is approximately 1 over square root of 3. So this is approximately K eta over square root of 3. Eta is oscillating with eta for a particular K mode. Next, so eta star, when you feel eta, some modes will be going through a maximum, and cosine is equal to 0 or pi or n pi. And when cosine is equal to n plus 1 pi by 2, then it will be going through the 0. And so CMB peaks correspond to, so both densities and velocities contribute to CMB peaks. So the dominant mode for CMB is the density. What we are seeing is the density, where so this cosine mode. Right? So the velocity mode, it introduces some Doppler shifts that shift the peaks a little bit. But the dominant part is still the density mode. So the CMB peaks you see when this K eta by root 3 is approximately equal to pi. That will be the first peak after the half oscillation. So eta at recombination is approximately, you can calculate, 278 megaparsecs. You put in all the parameters and calculate conformal time. The 278 megaparsec, 4 megaparsec at the time of recombination. Which means that for this equal to pi, the K has to be equal to 0.0195 megaparsec inverse, or lambda is 2 pi over K. So the scale which peak, which this first peak occurs, is of order 320 megaparsecs. But if you have looked at DO literature, they don't talk about 320 megaparsec, right? They talk about some other number. And that is because in the BAOs, we don't see the density mode, we see the velocity mode. And so we are almost running out of time, so let me just explain. So this has, I think, diagram please. Again, so the references for the BAOs is the original reference is this Sonier and Zeldovich, 1970 paper. The title of the paper is, this is in a Russian journal, AP and SS. The title of the paper is Small Scale Fluctuations of Rabbit radiation. And the more later paper is Eisenstein and Wu. So they explain very nicely, analytically, the BAOs, 1998. Right, so what is happening? So this is interesting physics. I just want to, I think, go through this before we finish. What is happening at redshift of 1100? Right, the photons decouple, universe recombines, photons decouple from the baryons, and they are just traveling, free streaming to us at the speed of light. Right? But baryons were going acoustic oscillations, so they were oscillating. Right? And oscillations means that there were density fluctuations as well as velocity. and they had also some finite peculiar velocities at the time of recombination. So suddenly the photon pressure disappears, and photons find themselves, if you look at one particular K mode, the picture here. If you look at one particular velocity K mode, okay, it will be something like this. So if you look at the velocity mode of baryons at the time of recombination, so they are moving with some velocity. So here we have bigger velocity, then it smaller again, it goes to 0, then it changes sign here. Right? It is bigger, then it becomes smaller, then again it changes sign here, and it becomes in this direction again. Again it goes to 0, and again it changes sign. Right? So now the pressure has disappeared, and this is the bulk flow of the baryons, all are going together, so they will keep moving. They will keep moving until these peculiar velocities, they will redshift as 1 over A. So until they are redshifted away due to expansion, they will keep moving in the direction they were moving, which means that in the places where, let us see, so in this place, here velocity was in this direction, and here the velocity was in the change sign, so it was in the opposite direction. So the flow is towards each other. So you will actually make a new overdensity here. Right? So you will have a new overdensity. And in this place, they are moving away from each other. So here the velocity is in this direction, this is again. And so here you will have a new underdensity. Right? And so on and so forth. It turns out that these new overdensities and underdensities, which are created after the recombination, they dominate over the density modes. And so density was oscillating as cosine, this is sine, so there is a phase shift of pi by 2. So it means that the modes which have the maximum amplitude in velocity, right, they have a minimum amplitude or zero amplitude in density, and vice versa, right? Because there is pi by 2 difference. When you have a peak of cosine, you have a zero of sine. So because this mode dominates, so what you see in DAOs is actually the sine mode and not the cosine mode. So there is a phase shift. And the first mode, so this theory that I am saying is valid only at sub-horizon scales. So it means that the first peak that you will see is not pi by 2, because pi by 2 is too close to, the first peak of sine is pi by 2, it is too close to horizon. So things are not really oscillating yet. They are just starting, enter the horizon, and then just started to collapse, but then the universe recombines and you stop. So the first peak actually happens not pi by 2, but 3 pi by 2. The first peak will happen at, so this will be K C S theta, or K theta over root 3 to equal to 3 pi by 2. And so this is slightly larger K, which means smaller scales. The first peak in DAO is actually at a slightly smaller scale compared to the CMB peak. So if you calculate this, you will get K of around 0.03 megaparsec inverse, or lambda of 200 megaparsec. Okay, so this is a rough number. If you do your density also contributes, right? So you have a mixture of sine and cosine in both CMB and but the dominant mode is sine, and then cosine will cause just the shift, small shift in the DAOs for the densities, a small phase shift. But it is roughly of order 200. The exact number, if you do exact calculation, it comes down to I think 150 megaparsec instead of 200 megaparsec. But the idea is same. So this is just the physics of DAO, and once it turns out this DAO peaks, the position of the peaks is relatively robust to astrophysics that people have seen in galaxy surveys. So it should be true for 21 centimeter also. But again, there have not been too many detailed studies with 21 centimeters, so that is again an open problem. And how robust it is. But the amplitude is usually more sensitive to astrophysics, because amplitude you can change drastically by just changing the spin temperature. But the scale at which the peak happens, that is usually more robust. right? And the way to then how you, after that is just, I think, simple calculation. So once you measure the BAO so going from BAO to dark energy is not too difficult. So what we observe is not K mode, but the angles, right? But we see not, we cannot really see the physical distances. What we measure is the angles. That, okay, two galaxies are some angle apart. So in 21 centimeters, we measure CLs, or the peak happens at some angular scale. So you measure theta observed, which is some angular scale. So you can calculate from there. The angular scale will be is R star, the scale of the acoustic peak, divided by the angular diameter distance, right? That is where R star corresponds to this K mode. So R star is just this lambda here, 200 megaparsec or 150 megaparsec, where that first peak is, right? So that is R star, and dA is the function of redshift, that particular redshift, that is the angular diameter distance. Then you will see it, this will be the observable, right? And you want to infer what R star is. Oh, sorry, what you want to measure dA from it. That is how it is standard rule. So R star we know where it should be because we have measured it in CMB, right? And so the BAO scale is related to the CMB scale by just the linear physics. Plus, you can introduce do some simulations, incorporate some baryonic physics also for small shifts in R star. Right? But this you can, it is a function of standard cosmological parameters. Right? So assuming this we know, or if it is not, then these are also free parameters that we will fit to the data. But assuming we know this accurately enough, we measure this, then we can infer dA. Right? And dA has all the expansion history. It is just the co-moving angular diameter distance is just the integral of the Hubble. Right? The R star is just the scale, the acoustic scale at recombination, that is this definition. So this is just integral of, so R star is the integral of the Hubble with a sound speed factor from recombination up to infinity, up to time zero. Right? And angular diameter distance is wherever we are measuring this up to redshift 0. And so both have this Hubble. So R star is actually sensitive to the early expansion history of the universe, whereas dA has information about the late time. Right? So the same thing for CMB also. So that is why you see solutions to Hubble tension involving early dark energy and late dark energy. So late dark energy will change this, early dark energy will change this. But assuming all this is standard, then this is the standard ruler. So you measure dA at different redshifts, and you can map out the expansion history. And H of Z is nothing but so it is omega radiation 1 plus Z to the 4 omega naught 1 plus Z cube plus some dark energy with some unknown dependence on redshift. So we can measure both this and this. And this is 1/2, or we can just put square here. So you can map out the expansion history, and assuming this and this is known, then you can infer both this and this, the evolution of dark energy. This is the, okay, I think run out of time, 4:30. Okay, so I think I will just stop here. Thank you.